Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Good to see you guys. Someone else is trying to get in here. Guys in. Okay. Let's see here. Ugh. Okay. Still trickling in here. All right, let's get to it. Plan for today is to just get through a bunch of examples that we're not even going to finish, but we'll try to make as big a dent in these as possible. It's going to go a little bit slower than normal, but that's because I'll be like explaining certain ideas and concepts and things to look out for as we go through them. To give a quick, very quick recap though, we talk about derivative rules and formulas, so we know what derivative is, why it's important. However, it's kind of annoying to use the definition of the derivative all the time. So now we want to use properties and formulas to find derivatives quicker, nicer, easier, especially for functions that we're very familiar with, like polynomials and exponentials and logarithms. We have some properties like the constant factor property. We can factor constants in and out of derivatives. Derivatives distribute across sums. So if I want to take the derivative of a sum of things, I can just take the derivatives of each one individually. We had a gap in our knowledge when it comes to multiplications and divisions of functions, but we fixed that last class with the product and the quotient rule. We also looked at rules for differentiating certain kinds of functions, like a general exponential function, the natural exponential function. We looked at the chain rule, very, very super duper important rule. This is a rule that allows us to differentiate composite functions, which is when you take one function, you plug inside of another function. How do you differentiate that new function that was created? And the idea is you differentiate the outer function, leaving the inside alone intact for the time being, and then you multiply by the derivative of the inside function. So that was basically the chain rule. Did a few examples there. We generalized some rules that we had with the chain rule. And as I mentioned, I would recommend that if you wanted to memorize any rules, you should memorize the chain rule version. They automatically include the basic versions, because if we replace u with x, then your u prime becomes 1, and then all the rules just default to the basic version with x. So u is a lot more general. U can be a whole bunch of stuff included in u. So knowing how to deal with it if there's a u there is nicer. Did some examples of that. We also looked at the derivative of the natural log. Derivative of ln x is 1 over x. Of course, if you apply the chain rule to this, this means the derivative of the log of anything is the derivative of that thing over the thing itself. And we did that example. And then moving on to last class, we looked at some other rules, like the power rule, how we differentiate power functions like x to the n. We actually use logarithms and implicit differentiation to figure that out, but we'll talk about implicit differentiation. It's pretty much the chain rule. We use the chain rule to figure that out. So that was the power rule. We could derive a lot of the previous rules that we had a lot easier. And of course, with knowing that we can distribute across sums and things of that sort, we can rewrite things to figure out what the derivatives are. We also looked at the product rule. This is how we're going to differentiate a product of functions. Like if I have a function f times a function g, the rule is differentiate one, leave the other, plus leave the first one, differentiate the second one. I would probably do it in this order all the time and memorize the rule in this order, because we also saw another rule, which is the quotient rule, how to differentiate a division of functions. And in this one, the order does matter. It has to be the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So I would recommend that you remember both of these rules sort of in the same order. F prime g plus fg prime. And just know for the quotient rule, you change the middle sign to negative and divide by g squared. And then we had a bunch of examples, and we had some announcements on a quiz and test coming up. So that leads us to where we are right now. So we're going to go through all these examples to just get extra prepared for the test that's coming up, which, by the way, is on March 19th during class. So that's this Friday. So this Friday, you'll log into Gradescope instead of logging into class, and you will take the test. And the test will cover, if you look through the syllabus, all topics 1 through 12. and topic 13 as a bonus. In regards to practicing for the test, I would recommend you go through the review on the class website. And then also, if you may or may not have noticed, because it came live this morning at some point, in Gradescope, I have a mock test for you guys, just for you to practice actually taking a test in Gradescope. I do not suggest that you take that right away. I suggest that you study regularly, you go through the review that was on the class website, and take a day or two and study, and then take the mock exam that I put on Gradescope. There's a mock test 1. Take it for realsies, right? So you just pretend that's the real test, and you take it and see how you do. So don't use anything that you wouldn't be allowed to use in the real test or anything of that sort. But just practice, and you'll get to practice uploading your work, because for the test you will have to scan or take pictures of your work and upload it to Gradescope. So you'll want to get practice of that. So the mock test is going to be open until, I believe, the night before your exam, midnight. And once you actually click on it, you have a finite window. I forgot what it was at the moment, like 70 minutes or 75 minutes or something like that. And yeah, so don't just open it and look at it, because once you open it and 75 minutes are up, you won't be able to open it again. So the point is to take it as a real test. Yeah, I think that's all I want to say for now, other than the fact that homework is due this week. So it's one of the major homework deadlines. All sections up to 3.4 should be done this week. And I believe that is also due like the night before your test. In regards to that, any questions on that? No? Okay, so we're good. But go through the review on the class webpage, and then, yeah, should we give you good practice? So what we're going to do now is we're going to just try to put a dent in some of these examples right here. And yeah, get us used to applying the rules. And of course, you should already have been applying them, because there were some problems on the quiz that you had to apply the rules for. So let's do that. So example 1. So it was y equals x cubed e to the x, right? And we want to differentiate these guys, right? So that was our first one. So you look at something like this, the first thing you want to notice is that it is a product of 2 functions, right? So that's one function, that's another function. I can think of this as f, I can think of that as g. So one, I would notice that I can't really simplify this or change anything, which is going to be important later. So I would just jump right into the product rule. So product of functions. So I'm going to do the product rule. So the product rule says, call this y prime because I'm finding the derivative, that I'm going to differentiate the first one, leave the second one, plus leave the first one, differentiate the second one. So this here is your f prime, this here is your g, this here is your f, this here is your g prime. This is the product rule. And that is in fact the answer. Now, of course, you can simplify this. Something like x squared e to the x is a common term. You can factor out 3 plus x, looks like.
Would you take the first version on a test, or would you require the second one, the simplified one?
It depends. So remember on your test, you might have multiple options. So I would expect you to know which option is which, right? So if you did this and you got the top answer, but in the multiple choice section, the bottom one is a possible answer, I expect you to recognize that those are the same thing. You might not have to write down that it simplifies to the same thing, but I expect you to know that. Very often I'll ask you to simplify stuff when you have like a fraction, right? So if you just have a list of things just spread out in one line, I don't particularly care about factoring it out or anything like that. I really care about factoring if it's like you have a ratio and you want to factor and cancel stuff, right? Then there's a point to factoring, right? As opposed to just making it look a little prettier. There's actually a benefit. But yeah, so in general, I mean, a problem will say to simplify. If it doesn't say to simplify, then you don't have to. But also, if you're given choices, you should be able to recognize what answers are equivalent to yours if they've been simplified or not. So hopefully that's clear. Let's go to a second one. Square root of x e to the x. So again, same idea. Again, I would think product rule here, because I have a product of functions. So I know from the product rule that my y prime is going to be f prime times g plus f times g prime. So this means that my y prime is f prime, which we know is 1 over 2 rad x, times g plus f times g prime. And that's that. That would be the answer. I mean, or you could simplify this as well. Something like 1 over 2 rad x e to the x times 1 plus x erase 1 plus 2x. Okay. Yeah. Also recall, we learned the power rule last time. This was the one that says the derivative of x to the n, where n is a constant, is nx to the n minus 1. And so if we forgot, for whatever reason, that the d dx of the square root of x was 1 over 2 rad x, we could do d dx of rad x is just d dx of x to the 1/2, and then apply the power rule. Which, I mean, again, or you could have that as 1 over 2 rad x. And so basically, I just want you to remember the rules are templates. They tell you what's allowed, what you can do. So if you're stuck on something, chances are there's a rule that you don't know. Okay, so there are a couple types of mistakes that you can make, like in a math class, generally speaking. One, you can just get stuck and not know what you should be doing. Whenever that's the case, it means that there's a rule that you're forgetting, right? So you need to go back and look at the rule, and then you have to try to use your algebra skills to change what you have, like this guy, to look more like a rule that you have, which is that guy. So you want to be able to rewrite things to look like the rules. So that's one thing, right? The other kind of mistake is you kind of know what to do, but you made some sort of silly mistake in computation or something like that. Yeah. So the rules are templates. And we And if stuck, we should try to rewrite what we have to look like a rule. So often, for example, we often want to write radicals as powers to be able to use the power rule. Okay, as you could do here, had you forgotten the rule for the square root of x. But a lot of students remember the rule for the square root of x. I'm just pointing out that this is something that you should be considering all the time. So if instead I saw like a 7th root, right, then I would definitely use the power rule. Like I don't have that memorized. Like why would I have that memorized? But yeah, so just be aware of that. Let's go to another one. And again, no, the product rule looks like that's one function, that's another one. So this is 6x times ln x plus 3x squared times 1 over x. This will cancel into that. And so this is 6x ln x plus 3x. Or I guess you could factor out a 3x, get 2 ln x plus 1. Nothing much to say about that one, I don't think. Here's one, though. How would you do this one? Are you guys there? Y equals x times radical x, what would you do?
I originally did product rule, but I'm realizing now, could you combine them if you wanted to, and then do power rule?
Yeah. How would you combine them? Because I mean, this is x times x to the 1/2, right?
You would add the exponents, and you would get
Right.
3/2.
Yeah, and now your y prime is 3 over 2 x to the 1/2. Right? Now, I want to mention here, versus, you may have been tempted to use the product rule right away. Right? And I mean, so you would have y equals x times radical x. And then you would say, well, my y prime is going to be the derivative of x times radical x plus x times 1 over 2 rad x. And then you're going to realize, well, that's just radical x plus, this is radical x over 2. And so this is going to be 3 over 2 rad x, which is, you know, your 3 over 2 x to the 1/2, which is what we got last time, right? So it is correct. However, Would not recommend this way, right? Nothing too crazy here. But it's, especially if someone knows how to simplify very well and combine those radicals and things of that sort. Because if I was given this on a test, that would be my multiple choice answer, 3 over 2 x to the 1/2 or 3 over 2 radical x. Whereas someone who does the product rule, they have to be able to see that that is actually the same thing, which is a little bit harder. It'll take you a little bit more work. So it illustrates the potential difficulty or potential issues in using product rule when you don't have to. So it turns out the chain rule is actually a very nice rule. I often, not often. A lot of students just have an intuitive feel for when the chain rule would apply. But there, every now and then I get a question from students that they're like, so when do I use the chain rule? Like, when should I use the chain rule? And pretty much the answer is going to be, you can use it all the time if you want. Like if you don't know when to use the chain rule, just use it all the time. There's no, it can't hurt you. Worst case scenario, you multiply by a 1. That's the chain rule. That's the worst case scenario. You apply the chain rule when technically you didn't need to. When it comes to the product rule and the quotient rule, however, this is not the case. These guys, they have a very expansive formula. So you can actually get into a situation where it's actually harder to simplify down to something that you'd want to, that's usable to you before you can use that information somewhere else, right? So don't use the product and the quotient rule willy-nilly. Here I'll give you like a pro tip. Generally, we want to apply lower level rules before higher level ones. This is true between disciplines. It's actually a general life hack, to believe it or not. Like, you can take this idea everywhere, but you know, it's kind of like Einstein said, things should be made simple, but not simpler than they have to be. But that is the case. You never want to, you see a problem and it just reminds you of this sophisticated rule that you know, and so you just mindlessly run into the rule. You have to have a little bit of discernment, a little bit of deliberation. Sometimes you want to see, could I apply something that's at a lower level? For example, laws of exponents, just do a little bit of algebra, and then I don't need the product rule. I don't need to simplify. I can just get to the answer. So this can be true between disciplines. Example, algebra rules are lower level than calculus rules. So we'd tend to want to apply them first. What that means here, always check if you can simplify something before taking a derivative. This can also apply within disciplines. This can also apply within disciplines. So example, constant factor rule. Is lower level than product rule, right? So, for example, if I ask you to differentiate 7x cubed, and now you actually know the product rule, it turns out one of these functions is a constant. There's a lower level rule than the product rule that would work. So, thing is, product rule applies, but so does the constant factor rule. Use this first. Don't just automatically just, oh, it's a product, isn't it? It's 7 times x cubed. And I just know that if I have something times something, I do the product. No, it's one of the things is a constant, right? There's a lower level rule that applies here. Just leave the 7 alone and differentiate the x cubed, right? So you don't want to have to go through a derivative of the 7 times the x cubed plus the x cubed times plus the 7 times the derivative of the x cubed. Like, best case scenario, you are going to waste time writing out all this extra stuff. Worst case scenario, you're going to make a mistake because it's actually very common when students try to apply that the product or the quotient rule in a situation where one of the things are constants, they tend to forget conveniently or inconveniently so in the moment that the derivative of a constant is 0. I don't know why, but it happens all the time. I don't know why. But so a lot of times when you go with a more sophisticated rule, you actually end up in a situation where you make things so complicated that other simpler things slip out of your mind. You make a mistake, you make an error. The longer you're writing things down for, just the more chances that you're going to make a mistake on something. Why put yourself in that position? So you always want to just glance at something. What is the lowest level rule that I can get away with here? Yes, it's a product of functions. Technically, the product rule applies. But also, one of them is a constant. I have something that's lower level than a product rule to apply to the situation. I should apply that first. So that's just something that I would say in general. So for this one, yes, a lot of people would mindlessly jump into this via the product rule, and it's not wrong. You can get the right answer. And for this particular example, it's not totally so crazy. However, what are the chances Jhevon is going to give you an example like this on a test, right? On a test, it's going to be a little bit more complicated. And then the detour you would have to take by applying something like the product rule when you really don't have to is just not going to be worth it at the end of the day. So you always want to look at something and see, can I kind of finagle this a little bit before I try to apply some general sophisticated rule, right? Moving on, where are we? 5. Now this one can be simplified, but this one is actually, it's not even quite worth it. However, I would feel like most students wouldn't even recognize that this could simplify, so I'm not going to sweat it too much. I mean, we could simplify this. Most students won't recognize how, though. Does anyone actually see how to simplify this? And simplifying something like this isn't important in this class. It would be in a Calc 2 class, but chances are if you're in this class, you're probably not taking Calc 2. But the idea would be to, you could do long division of polynomials. That's one option. Another option is try to get the numerator in the top. So I can add and subtract 2. Why? Because I want this, the denominator to be in the numerator. This would mean that I have x plus 2 minus 1 over x plus 2. And then I can break this into 2 separate fractions. It ends up being 1 over x plus 2. Or you can think of it as 1 minus x plus 2 to the minus 1. In which case, derivative of the 1 is going to be 0. The derivative of the other guy is going to be, you bring the minus down, subtract 1 from the power, multiply that derivative of the inside, which is 1. So that's actually going to be easy to see that the derivative of this is actually going to be x plus 2 to the minus 2 minus second power. Okay. But at this point, like if you didn't see that, I really wouldn't sweat it. Simplifications like that aren't particularly necessary in this course. However, so I would see a division. So this is a quotient, right? I have x plus 1 over x plus 2. That's like my f over g. And so I want to do the quotient rule. So this is going to mean y prime is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And that's because what I just did was this is f prime times g minus f times g prime over g squared. Now we can simplify. This is x plus 2 minus x minus 1 over x plus 2 squared. That gives you 1 over x plus 2 squared, which is what we said would have been the answer, x plus 2 to the minus 2. So this is applying the quotient rule. Okay, here's another division. How do we do this one?
I did the quotient rule here.
Okay, and what did you get?
2x over 3. A long way.
Okay. So that is the correct answer. But in light of what we did today, can you think of another way?
I'm guessing the power rule.
How would you apply the power rule?
Would you do x squared times 3 to the negative first power? Or
I mean, you could factor this off as a third, right? Which is 3 to the negative first power, I guess. And then you just apply the power rule. So this stays and that becomes 2x. You get 2x over 3. Okay. Versus you actually doing the quotient rule. And so what did you get here? What did you do?
I got 2x times 3 minus x squared times 0 all over 9.
Right. Now, here's the thing with something like this. You didn't make that mistake, which was very good, but students often miss this, especially in a test. Turns out, for whatever reason, how the human brain works, when you're rushing in an exam, it's very easy to forget that 0. But yeah, So you would do that, and then you would see, okay, that's 6x, well, minus 0 over 3 squared, or 6x over 9, and then you can reduce this 3 into each. So 3 into that goes 2 times, 3 into that goes 3 times. Again, in this case, it's not that bad, but I would much rather you do the way on the left than the way on the right in this situation. And in fact, I will say this as a pro tip. For d dx of f over g, if g is a constant, just leave it alone and differentiate f. That's it. And the reason why that works is the same reason why it works here, because I could factor that g off to the side, and it's a constant, so it's just going to stay. So I'm just going to leave it alone, because that's what the constant factor would tell me. And then I can differentiate the function part. And of course, afterwards, I can multiply back, and the g just goes back underneath, right? So there's no actual need to actually do a quotient rule here. So in fact, if I see here the derivative of x squared over 3, all I do is leave the 3, differentiate the x squared on top. Look at that. There's the answer right away, right? It's a short, like I could literally do it in my head. It's the shortest way so far, right? I just literally differentiate the top. Only needed to differentiate the numerator since denominator is constant, right? So quotient rule was not needed, right? I didn't even think of this as the quotient rule. Okay. So little things like this, they add up. You know what I mean? I mean, so far, I mean, I'm giving you simple examples just to illustrate the point. So you're not even going to really see the benefit of what I'm telling you right now. But I can tell you, even with the little benefit that we're seeing so far, trust me, it adds up on an exam, right? Like you're in an exam, and if you count each individual item of each individual question, you're doing like 20, 25 problems, 25 individual problems. If you're inefficient on every one of them, it adds up. It slows you down. It introduces causes for opportunities for mistakes. It gets your brain more tired. Like there are so many things that not being efficient can affect you with, right? So how do you fight that efficiency? It's just know when you don't actually need a rule, even though technically you could apply it. When is something overkill? Try to apply the simplest thing before applying a hard thing. And because of the constant factor rule, if some part of some larger system is a constant, you can kind of try to see, can I view it in the lens of the constant factor rule as opposed to something at a higher level, like the quotient rule or the product rule. So we would not use it. So we would not use quotient rule in this situation. Not because it's wrong, but because, I mean, it's overkill, right? Which is just, it's a bad way to live your life in general, but for practical reasons in a math class, it's a bad idea because all those little inefficiencies, they add up and they affect you when it counts, right? So you don't want to go too hard. It's not always about go hard or go home or work harder. A lot of times it's about working smarter, right? Being more efficient. Let's go with another one, 7. What do we do here?
bring the radical to the top and then just use product rule? I mean, power rule.
Yeah, we don't even need a product rule anymore. Now it's constant factor rule. I can literally just see that it's minus 3 over 2, x to the minus 1 over 2. Yeah. Versus quotient rule. The bottom times the top. Again, students often forget that 0, but I won't. Minus the top times the derivative of the bottom over the bottom squared. Now you do that on a test. Are you immediately going to realize that it is the same as that answer that I have on the left, which is probably what I would do in an answer choice, because it's easier to type the answer on the left than it would be to type the answer on the right. So now you're going to have to worry about, all right, so this becomes that. Okay, how do I simplify that? I don't know. I guess I can multiply by 2 rad x over 2 rad x. So that would be minus 3 on top of 2x rad x. Sorry, yes. I actually made a mistake on this one. That should be a 3 over 2. Because subtract 1 is subtracting 2 over 2. So it's 3 over 2. And so now you would see this as minus 3 over 2x to the 3 over 2, right? Which now looks like that. But I mean, conceptually, psychologically, like you wouldn't want to go through that on a test. It's much easier to just bring it up. So that's another pro tip, I would say. For d dx of f over g with f constant, do not use quotient rule. It's overkill. Rewrite as f times g to the negative 1 and apply constant factor rule. Okay, so some important concepts there. So here, like 8, we have 4 over x cubed, and now you already see where this is going. Hey, I can just realize that that's 4x to the minus 3. So the derivative is going to be minus 12x to the minus 4. Right? Don't need the quotient rule. Don't need to have to worry about simplifying stuff and multiplying and dividing by LCDs and all that stuff. That's just the answer. 9, y equals ln x divided by e to the x. Now here, can't really simplify here. So here I would just jump into the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Common mistake. This is e to the 2x, not e to the x squared. Remember, when you raise a power to another power, you multiply the powers. It'll make a difference. Now, what we can do is say factor off, say a 1 over x e to the x, have 1 minus x x ln x over e to the x Okay. This guy would cancel one of those, and the x can go in the denominator, so this just becomes 1 minus x ln x over x e to the x, which is probably how I would put the answer choice. So when it comes to fractions, usually you're going to want to simplify. Yeah, I guess that's it. 10, y equals e to the x times ln x. What do we do here?
Product rule.
Product rule, right? Our product of functions can't really simplify anything. This means y prime, differentiate the first one, leave the second, plus leave the first, differentiate the second. So that's that. You could also factor out stuff. Um, 11y equals x cubed plus 1 to the 20th. What do we do here? Multiply out the 20. No. Here, chain rule, right? Because there's an inside function here. So the chain rule says I would differentiate the outer function, which we can do by the power rule, leave the inside alone, then multiply by, open parentheses, the derivative of the inside. So this is 60x squared x cubed plus 1 to the 19. $12. How do we do this one?
E prime times U prime.
U prime times e to the u, right? So we know the derivative of e to the u is u prime e to the u. So I'm just going to differentiate the numerator, which is 3x squared, multiply by the original function. That's it. 13, y is ln of x cubed plus 2x plus 1. The rule that applies here is the derivative of ln of u is u prime over u. So that's what I'm going to do. I'm going to put that guy in the denominator, and on top, I'm going to put his derivative. Done. Let's get through a couple more. Minus x to the fourth. What I would do is I would think of this as 2 minus x to the fourth to the 1/2 maybe. Then you could do the chain rule. And I mean, you could simplify this if you want. 2x cubed times 2 minus x to the fourth to minus 1/2. Here, I'd apply quotient rule. Can't really simplify that. So it's going to be the bottom times the derivative of the top. minus top times the derivative of the bottom where the derivative of the bottom was done via chain rule, all over the bottom squared, which means I double the power. You will notice that in the top, x plus 4 is a common term. So I would factor out x plus 4. We learned in algebra class, you always factor out the lowest power. So I would be left here with x plus 4 minus 6 times x plus 1 all over x plus 4 to the 12th. All of this would cancel into those, leave you with a power of 7. And in the numerator, you would have minus 5x minus 2. By like expanding this. So this is x plus 4 minus 6x minus 6. Okay, one more and then we go. And of course, you guys should practice the rest on your own. Can practice them for this. I will say, for something like 19, you definitely want to simplify first. Don't just jump into the rule mindlessly. Remember your training grasshoppers. 16 y equals x divided by e to the x cubed. Quotient rule. Can't simplify. The bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And factor out an e to the x cubed, left with 1 minus 3x cubed. Eventually, you'll be able to do these relatively quickly if you practice enough. But yeah, I would say do the rest. I actually see you guys tomorrow as well. So we'll finish up the rest tomorrow. And maybe we can get into some of the stuff that you'd have to do for the bonus section. Do the rest for 19. Try to simplify first. But we'll stop there. So yeah, we'll get to the other examples next time, and then the next time after that is going to be your test, in which case you should log into Gradescope. Remember, there's a mock exam. Be sure to practice it. Be sure to go through the review on the class website before practicing the mock exam. And for now, that's it. I guess I will see you guys in the next one. Ciao.